And so let me delve right into it and outline what we're going to discuss today. And so what I'm going to be talking about is a very simple device, basically a single layer of semiconductor, a single layer of semiconductor which is sandwiched between two electrodes. One side is a cathode and the other side is an anode. And this is a simple energy diagram representation of what we are talking about. And in the first case, I'll talk about a device which is close to symmetrical, which has a symmetrical characteristics with the low injection barrier height at the anode, at the cathode, and a similar low injection barrier height at the cathode also. And we, so basically a single carrier device. It could be a hole only device when the barrier heights for injection of holes is very small. And similarly, we could have a device with the good injection characteristics at both cathode and anode for electrons. And so that would be an electron only device. So I'll start with a device like this. And many of you would recognize that we use such a device for example, for studying mobility. We make a hole only device and we measure the IV characteristics. And from there, we try to extract the transport parameters, the mobility of the semiconductor. So let me start with that. And then I'll come to, so this is basically a test structure. And then I'll come to devices which are asymmetrical, which have a built-in voltage. And these devices are used as rectifiers, as light emitting diodes and solar cells. So I'll talk about analysis of those particular devices. So let me start with this single layer device here and talk about estimation of mobility, right? So we all know that when we take a device like this, and for my discussion, I'll be focusing mostly on organic semiconductors. So when we take an organic semiconductor and sandwich it between two electrodes, both of them are, and we'll discuss hole only devices. So both of them are good injectors of holes. If the mobility is not, let's say, doesn't have a field dependence initially, let's say, this is a simple expression that we use for characterizing the current flow in a device like this. And if we measure the current voltage characteristics, we can see that there is a mobility term that is there. And most of the other terms are something that permittivity and the thickness are something that we know. And therefore, we could, in principle, by looking at these characteristics, we could extract the mobility in the semiconductor that is there here. The only problem is that most semiconductors that we encounter do not have a constant mobility. So let's take this expression and make it a little bit more accurate, where we take a common Poole-Frenkel kind of a mobility model. And so with this kind of a mobility model, a sort of a semi-empirical expression we can derive, which has this, the first term that you see here, the first term, the Mott-Gorney's expression for space charge limited current, modified by the field dependence of mobility here. So this was the expression which was suggested in 1970 by Murgatroyd. And this is a popular expression that is used for extracting the mobility parameters. So we have two mobility parameters, the low field mobility mu naught and the field enhancement parameter gamma. And if we accept this particular expression, then what we can do is we can take J divided by V square, take a log of it. So we can have ln J by V square. And then the right hand side is a constant plus this particular term here. So what we see here is that if I were to plot ln J by V square here against the, let's say, the average field in the device, V by D, what I expect is, if this particular model is correct, what I expect is a straight line, and from the slope of which I can get this field enhancement factor, and from the enhancement and from the intercept, I can get this factor K1, which is all this term here, and I can get the low field mobility. And so let's see how well this particular model works here. So I'm going to use a mix of simulation and experimental results to illustrate the points that I'm going to make. So if I take an expression like this, let me first show you a simulation result. So if I take a single layer device with good hole injection from both sides, and I determine its IV characteristics, and I apply this particular model, right? So when I apply this particular model, this is the typical graph that I get here. This is the typical plot that I get here. Note that on the right hand side I have ln j by v square, the right hand side, and on the x-axis we have v by l here. V by d or d and l are being used interchangeably, the thickness of the device here. So we expected a straight line. But what we get here, as you can see here, is more like a V-shaped, a tilted V kind of a characteristics here. And very often what people do is they sort of ignore this particular part here and they take a portion where perhaps a straight line can be fitted, and they try to extract the low field mobility and gamma from these characteristics. And but when we do that, for example, we've taken a simulation data, and so we know exactly what the low field mobility and gamma are. But when we apply this particular method and we try to extract those parameters, we find that there is a large error here. So this shows the error in the estimation of low field mobility value, mu0. And so first, as we can see here, this is not a very good straight line. And therefore, it depends on where you draw the tangent and try to estimate the slopes and all that. So if we take a range from 3 to 4 volt range here, we get an error which is more than 100%. If we go to 4 to 5 volt, we get an error 88%. And even at 5 to 6 volt, we get an error which is about 70% here. Right? So this is the error in mu0. And in the field enhancement factor also, if we go, the errors are not as large, but still in the 3 to 4 volt range, the error is 24% and gradually comes down as you go to higher voltages here. So obviously we were expecting a straight line, but the characteristics of the device are more complicated than what the model indicates, and that's why these errors are there. And therefore, if we use this particular method to estimate the values that we will get will be fairly off. So what is the source of this particular error here? Well, if we take the device that we are talking about, a symmetrical device with good injection characteristics, if we take it as a field independent device, we expected the characteristics to be of this kind here, the space charge limited current described by Montgomery expression here with a V square by D cube. And with a constant mobility also, when we actually simulate, we see the characteristics are shown in this red here. And these difference comes about because of the expression that you see here neglects diffusion, and the discrepancy is largely because of that. And so this expression, which is the source of Murgatroyd expression for current under field dependent mobility, the starting expression itself is flawed and requires correction. And so as I indicated, the major reason is that we are neglecting diffusion. And one of the consequences is that if you take a simple semiconductor device, let's say at equilibrium, undoped semiconductor device at equilibrium, and if you analyze it, what you find is that it already has, even though you have not applied any voltage, not injected any carriers as a result of the voltage here, you already have a lot of carriers that are there inside the device here. This shows the characteristics, hole concentration inside the device at equilibrium. So you find that there are a lot of holes already there, and these holes have basically diffused from the contacts, from the anode side and from the cathode side here, and that's why you see high concentration close to the cathode and the anode, and you see this kind of a characteristics here. And therefore, when you apply a voltage, what happens is these carriers, then they move. And what you end up getting is basically a linear, an ohmic current here. And I'm not going to go into the details, but one could model the ohmic current through this particular expression here. So what you see is that J varies linearly with voltage. It's still 1 over D cube. And you have the other terms that are there dependent on mobility. And so what it has been suggested is that apart from carriers that come in from injection, there are already carriers that are there at equilibrium that have come through the diffusive process here. And what has been suggested is that a better expression for current would be the usual Montgomery expression that you see here. And if sort of you add this extra term there, these extra carriers that are there that came in through the contact and contribute to a linear component here. And so this model is an improved model that has been suggested for the space charge limited current in the case where we have good injection from both the sides here, for a symmetrical device here. Now, the trouble is that, yes, this expression, if you try and, fit your data with this kind of an expression, you get much better match. But the trouble is that the devices that we make are not exactly symmetrical, in the sense that it's unlikely that the barrier height for injection from the cathode and the anode are exactly the same. More likely is that there's a little bit of asymmetry also, even though you try to ensure that there's a good injection from both sides. But because you're using different contacts at these two places, there's likely to be an asymmetry. So let me show you a device which is also, which has reasonable injection from both sides, but there's a bit of asymmetry here. So the injection barrier height for holes here is taken as 0, but the injection barrier height from the other side is taken as 0.3 eV. So here is the hole density graph at, when injection barrier height from both sides is 0. And this is when the injection barrier height from the cathode side is a little bit higher, which is 0.3. So what we see is that there's an asymmetry in the hole density at equilibrium as compared to the symmetrical case here. And that sort of brings into question, is this expression then really correct? Because this expression was derived for a completely symmetrical characteristics with this kind of a hole density profile here. While, when we have a little bit of asymmetry, then the characteristics are different. And then this calls into question whether an expression like this is valid. So our analysis has shown that yes, the asymmetry, the previous expression is not strictly correct. But if we look at this asymmetry here, what we found was that if you look at this particular graph for 0.3 eV here, if you artificially extend the length of the device here, the graph again becomes sort of symmetrical, except that the length of the device is not taken as the earlier, let's say 100 nanometer, but if you extend artificially the length of the device, then the nature of the graph is similar to what it was before for a completely symmetrical characteristics. So we studied that for a variety of injection barrier heights, and we found that this particular picture seems reasonable. And so what we suggested was that the current, even in cases where there's slight asymmetry, the current can still be modeled by the expression that was suggested in the past, but with a modified effective thickness of the device here. So it's not just D, but there's an additional D dash that you can add here to sort of model what the current in the device is. So effective current, so that can take care of the asymmetry part that is there here. And D dash would of course depend on how much asymmetry is there here. So what we suggest is that this standard Mott-Gurney expression that is there here to begin with should be modified to this kind of an expression. There is this particular term which is there, but then there is this additional term, the ohmic term here, which can be modeled by with an expression that we just looked at with a V divided by D plus D dash cube here. And we can combine these two terms together into a more compact term, which is 9 by 8 epsilon mu p V times V plus V beta by D cube here, where V beta is an additional term, which we can write it in this particular form. If I had a completely symmetrical device with barrier heights from both sides being equal, then this term D dash would have been 0, and this V beta term would have an ideal value of 0.91. But in an experimental device where such a situation may not be there, V beta may depart from 0.91. And let me show you how V beta may change as a function of, let's say, when I change the cathode barrier height. So it starts from 0.9 here, but as the cathode barrier height increases, the value of V beta drops here. And so in an experimental device where I'm not really sure whether the barrier heights on both sides are the same or not, I do not really know what the value of V beta is. It could be 0.9, but it could be 0.7, it could be 0.6 also, depending on the nature of the contacts on the two sides here. But anyway, we have a starting expression which is a much better expression than the original Mott-Gurney expression here. So we can use this to derive, now we can add a mobility, field-dependent mobility part and derive a better expression for current, which takes into account the field-dependent mobility part here. So this is in contrast to the original expression that was proposed by Murgatroyd and which is commonly used in literature to estimate mobility. So what we suggest is that this is a better expression that one can use. It takes into account diffusion currents through this particular term here, V beta here. So our improved method for estimation of mobility is that what we now do is we plot ln j by not v squared, but v times v plus v beta here against the average field, which is v by d here. And once you do that, we know a ideal value of v beta, but the actual value of v beta, we try to extract it experimentally also. So I'll just talk about it in a minute. So, but if we use this improved expression, note that the plot now of the right-hand side versus left-hand side becomes much more linear here as compared to the previous plot that I just showed here, right? Which sort of tells us that the model is much more accurate. And if we try to use this particular model to estimate the mobility parameters, they're likely to be much more accurate. And so let me show you a simulation result first, where we took a asymmetrical case with a cathode barrier height of 0.3. And so we have a simulation data and we subject the simulation data to this particular expression. And what we try to do is we try to use this V beta as a tuning parameter to get a characteristic which is as linear as possible here, right? So we use this, we start with a value of V beta equal to 0.9, but we modify it to get a characteristics which is as linear as we could get through the variation of this one single term here. So we did that, and with that then we estimate the mobility parameters. And so what I'm showing here is the mobility parameters estimated using three different methods here. The original Murgatroyd method here, then the other one with a V beta with the ideal theoretical value of 0.9, and then V beta which is empirically determined. V beta which is empirically determined here. And this is the error in mu naught. So the error in mu naught, which used to be with Murgatroyd method, which used to be very high, more than 100%, drops significantly when we use this particular expression with an ideal value of V beta here. But this ideal value of V beta of 0.9 also gives us significant errors. But when we try to fit it with an empirically determined V beta, then the error drops significantly here. And whether we take 0.5 to 1 volt range or 1 to 2 volt range or 2 to 3 volt range here, the value of the errors are less than 10% in estimation of mu naught here. And similarly, the estimation of the field enhancement factor gamma also becomes much more accurate here. All right, so what we suggest is then let me show you an experimental result here. So that was the simulation data. So this is a single layer hole only device made using Pentacene with MOX on both sides. In one case is an aqueous MOX, and the other side is we have an evaporated moly oxide with a gold contact here. On the other side is an ITO. So this is like an ideal energy diagram. And when we measure its IV characteristics, both forward and reverse, we see that they are not exactly the same, but they're very close to each other. But we expect a little bit of asymmetry in the forward and the reverse characteristics, but it's a device with good injection of holes from both the sides. So we take this data, and when we subject it to the conventional analysis using Murgatroyd method here, note that we don't get a proper straight line, and so the extraction of mobility and its parameters becomes difficult. On the other hand, when we use our improved model that we discussed here, we get a straight line over a much larger range, and the extraction then becomes easier of the parameters here. So we empirically determine V beta of 0.88. As I said, the ideal value is 0.91, and here is 0.88. So the device is close to ideal here. And we determine mu naught and the other factors here, the field enhancement factor. But more than that, let me show you the data using our proposed method. These dark squares, they show the mobility values that were extracted using this method here. And note that mobility value extracted in 0.4 to 0.95 range or 0.95 to 1.3, these are the same mobility values here. As compared to the Murgatroyd method, because it's not a straight line here, So it depends on where you extract it. If you extract it in this particular range here, you get this mobility value. If you extract it in this particular range, you get a different mobility value. Similarly, our extraction of gamma also becomes much more accurate as compared to the previous approach here. So I'll quickly summarize. What we are suggesting is that instead of the standard Murgatroyd expression that is used for extraction of mobility, we suggest a improved expression for space charge limited current with field dependent mobility. And we suggest that plotting of ln J versus V by V plus V beta versus the average field will give you a much better estimation of low field mobility and the field enhancement factor that is there here. All right, so that's the first part which is there here, a method for better extraction of mobility. In the next case, what I'm going to do is take a device which is a rectifying device, where, for example, and I'm going to take a case where we have good hole injection from one side, but the other side, the barrier height is large, and you may not have, you don't have a good hole injection at all from here. But the barrier height could be high enough so that you may have an electron injection from the other side. So that could happen also. But in this case, when it's an asymmetrical device, you get a rectifying characteristics. And so let me show you a case here. So again, I'll start with some simulation, and then we'll look at some experimental results. So if I look at a device of this kind, where we have good hole injection from one side and we have the other metal, let's say this is like aluminum and this side is like gold, and we have either injection of holes or electrons, both are difficult from this particular side here, and a built-in voltage of 5 minus 4.1, we have about 0.9 volt here. So if I take a device like this and if I simulate, I get data, and this is the common way that people try to interpret the characteristics. We often plot the data on a linear plot, and or a log linear plot or a log plot. So these are the common ways that we display the data in order to understand what is happening in the device. And a linear data, a graph would show us that the current is that there is a threshold that we can see here. The current is very low, and then the current begins to increase. So sort of threshold, we can see existence of a threshold, which we don't see in a symmetrical device. In a log linear plot, we can see a clear two regime in the characteristics, and a straight line here indicates an exponential characteristics, and here indicates some kind of a power law that we expect, and sort of a two region behavior we can see here. And this, of course, log plot we commonly use to see whether we have a power law behavior, whether the traps exist in our device or not. So let's say this is device A. Now let me show you. So these are the conventional ways in which we try to understand through these plots here. Linear, log plots here. So let me show you a device B also. Right, so device B. And if we see the characteristics displayed using these three methods, we again, if you see device B, and focus your attention on B, and let me show you A, I don't think you would be able to notice any difference between A and B. Let me put A and B side by side here, a log plot here. So this is my device A, and this is my device B. And if you were to take a slope here and try to calculate, you won't see much differences here. So when you display characteristics like this, you would conclude that A and B are basically very similar devices here. And so my point is that these linear, log linear, and these ways of displaying data are inadequate if you want to understand the devices properly. And what we suggest is a very simple tool here, which is simply the derivative of the log plot. If you use the derivative of the log plot rather than the log plot itself, and let me show you for A and B, what you see is this here. This is the derivative of log plot of A. And we call this derivative, just to give it a symbol G, because it's the ratio of a small signal conductance by DC conductance. So because of the conductance terms that are there, it's a ratio of two conductances. That's why we use the symbol G here. So anyway, so if you take it derivative of log, this is the signature that you get of the device A. And on the other hand, if you take of B, you find that there is an additional peak that you see here. So here you see a single peak here, and here you see two peaks here. And what I will just show here is that, since these are simulation results, so I know exactly what has been done. So device A is an ideal device with no traps, simple single semiconductor sandwiched between two electrodes here. While in device B, what we did was we added a trap located at 0.5 eV above the valence band with a concentration of 2 × 10⁻16. And so what is happening is that this first peak that you see here is due to the presence of built-in voltage inside the device. The second peak that you see here you see two peaks. One peak is due to the built-in voltage, and the second peak is because of the presence of a discrete trap. So let me come to the built-in voltage first here. And so when, it's very common when one measures these devices, rectifying devices, we get a characteristic like this here. At low voltages, we get a shunt resistance, a linear behavior. Then we have an exponential characteristics, and then it goes towards a power law kind of a characteristics. And often for a quick estimation of built-in voltage, people tend to draw a straight line, fit a straight line here, fit a straight line here, and at the intersection of it, to calculate a threshold voltage or a sort of a built-in voltage for the device here. But note that these characteristics are not linear here. And on a log linear plot or on a log plot, these are not linear here. So fitting a straight line is problematic. It also depends on at which point do you draw a straight line. And therefore, determination of a threshold point or a built-in voltage using this particular method leads to ambiguities. On the other hand, if we just simply take the this function here, the derivative of the log plot, if we apply this particular function to the exponential characteristics, we get basically a linear behavior. G should be equal to some constant times V. And if we apply it to this part here, power law part here, we get G equal to M V by V minus V alpha here. So if we look at, instead of drawing these, fitting these tangents here and trying to see where the transition point is, this function here reveals the transition point much more accurately and in an easy manner here. So let me show you here. So if I look at the function G, the exponential characteristics give rise to a linear line like this here, as I just indicated, while the power law characteristics gives rise to an expression of this kind, M by V minus V alpha here. So note that as voltage comes close to the threshold point, this particular function tends to blow up here. And so the two together then give rise to a well-defined peak in the characteristics. So if you determine the derivative of the log plot it against V here, it nicely indicates the transition point as a peak in the characteristics. And what we can show, so this is the, the actual characteristics. And if you take the derivative, you see this particular peak here. And you can determine this quantity called this V alpha here, the place where the peak occurs. And through simulation results, we have shown, this is G for various values of built-in voltage, 0.6, 0.8, 1.1. We show that this peak value here, V alpha, scales linearly with the built-in voltage here. It scales linearly, and after lots of simulations, we could fit this particular expression that you see here. V alpha is 0.925, VBI minus 0.25. So the idea is that you measure your experimental characteristics, take the log derivative, find out what is the value of V alpha, and use this particular expression to get an estimate for the built-in voltage that is there. All right, so that's a quick estimation of built-in voltage. I'll skip this particular part here. So coming back to our device B. So the first peak, as we said, is the peak due to built-in voltage here. The second peak, as I said, is because of the traps. Now, why do traps result in a peak in this particular, when you take the derivative of log function here? So that can be understood through this very simple diagram here. So what happens is, so this is the energy diagram here, and this is the dashed line shows you the trap level here. And so at low voltages, the Fermi energy is above the trap level. Most of the traps are empty. Then as you apply increasing voltage here, more and more holes are injected. The Fermi energy then moves down, and eventually it comes close enough and starts to cross the trap level. At this particular point, the traps are filling up. Once you inject enough number of holes, the Fermi energy comes below the trap level here, and all the traps are full. So what happens is, when the traps are mostly unfilled, the characteristics are, if you look at the expression for current, Q mu P P E, the characteristics are like the space charge limited current with a slope of around 2 or so. But then once you reach a voltage where the Fermi energy is crossing the trap level here, now what is happening is you're modulating P also because of the changing trap occupancy. So P becomes a stronger function of voltage here, and so current starts rising rapidly here. But once you fill up all the traps, then again, then P again then only changes because of the injection, and the change in P with voltage again then becomes more linear type. And then again, it becomes the dependence of J on current becomes smaller here. So what you see here is that there's a sharp, once the traps are filling, there's a sharp change in current versus voltage characteristics. And once you take the derivative of it, where the traps are filling up, once the traps are filling up, you start to see a peak here. If the traps are not there, then this kind of a behavior is absent, and you won't see the presence of a peak. So the thing to keep in mind is that whenever the traps are filling up, if you take the derivative of the log-log plot, it would show up as a peak in my characteristics here. So this is, when you make let's say a asymmetrical device, rectifying device, this is the signature of a good healthy device here. Is sort of an ideal signature where you would see a single peak due to the built-in voltage here. On the other hand, if there are any abnormalities, they would show up as, for example, as additional peaks that you see over here. And the nature of the additional peak, you can gain a lot of information from there. You can sort of tell whether there is a shallow trap or whether there is a deep trap. You can sort of tell whether there is a Gaussian distribution of traps, or there is an exponential distribution of traps, because each one of them has its own unique signature. Each one of them has its own unique signature, and I'll quickly illustrate some of these. For example, in this case, what we did was we introduced a trap at one single energy level, but of different concentrations. So the black graph shows the ideal characteristics. And in the red graph that you see here, we introduce a trap at 0.5 eV. So the energy is the same, but with a concentration of 3 times 10 to the power 16. So this is where the additional trap peak is. In this case, we introduce a trap of 6 times 10 power 16. So the trap peak moves to higher voltage here. And in this case, we introduce 10 power 17. So the trap peak moves to even higher voltage here. And one can show that this peak value, it scales with the trap density that is there here, right? So the trap peaks here. Similarly, one can see what is the effect of the depth of the traps. If you have a shallow trap of 0.2 eV, it doesn't affect your characteristic. It doesn't show up because at these voltages here, the Fermi energy is not able to approach close to the trap level, and therefore, since trap occupancy is not modulated, it doesn't show up in our characteristics. So 0.2 EV does not result in any distortion. 0.4 EV results in this blue graph that you see here, distortion here. 0.6 EV is a deep trap. It results in even stronger distortion in the characteristics. These are the, so by analyzing the VBI peak versus the trap peak, the ratio of these two, we can sort of, guess how much is the depth of the traps that are there here. Similarly, for example, if you have a Gaussian distribution of traps rather than a single discrete trap, what you find is that the characteristics are more stretched out. So this red one shows a single discrete trap, while the green one shows when you have a Gaussian distribution of traps, so you get a stretching. And that is expected because then the trap filling is occurring over a larger period, because there are multiple traps located at different depths that have to be filled up. And so you see a stretching in the characteristics, which is even more visible when you have an exponential distribution of traps. In that case, when you have an exponential distribution of traps, you are never completely filling all the traps. And so what you see is you don't see a peak at all. You see you see a substantially higher value of this parameter G, and no significant sharp peak that you see here. So the point that I'm trying to say is that by simply taking a derivative of the log-log plot, you get a lot of information which is otherwise sort of obscure, which is not readily visible. You could tell whether there are traps present. You could tell whether there are exponential, discrete, or Gaussian distributed traps, and you could extract more information. If you have more than one trap, you could get more than one peak as well. So these are simulation results. So let me show you the experimental results. So this is an ITO P3HT aluminum device, a single layer device here. The black line shows you the experimental data. So this is a good device. What we see is a single peak, and no satellite peaks and all that are visible here. And the red one shows a match with the simulation results here. So if I use a VBI of 0.65, note that VBI of 0.65, I can simply calculate by finding where the peak of my graph is, and using the empirical expression that I described earlier, we can determine VBI. So with this VBI, if we simulate the characteristics, and we find that a fairly good match between simulation and the experimental data here. So as I said, once you make a device like this and you determine the derivative of the log-log plot, and you see something like this, that's an indication of a reasonably good device. On the other hand, if the device has problems, if the polymer has not been annealed properly, or if there's a degradation that is there, you start to see characters like this here. So the black one is the ideal device. This one is a device which was not annealed properly, and so you see an additional peak here. This is another, you see even more prominent peak that is there here. So you see these additional peaks. And let me describe this first, the red peak and the blue peak here. So this is the data here of a device which is that has not been optimized properly here. So you see this additional peak. This is the experimental characteristics. And when these are the simulation results when we use a simulation for a trap located at 0.38 eV with a concentration of 4.4 into 10 power 16. So you can see that the characteristics are very similar here. As I said, when you have a reasonably well-defined peak, it's an indication of a discrete trap. And but note that the trap concentration and the depth is not so high. Otherwise, it would have overwhelmed the VBI peak. The VBI peak is still fairly well-defined here. In the next case, note that there's a VBI peak and the trap peak. They are comparable in prominence. And the simulation results show that in this case, it's a deeper trap with a higher concentration of 5 times 10 power 16 here. All right, so let me show you some more data here. So this is a solar cell here, ITO P.PSS with the P3HT blend of P3HT, PCBM, and aluminum on one side. So again, I'm showing you results which are interesting from the point of view of that they show some traps. Either they are solar cells which have degraded, or solar cells which have not been optimized properly. So here you can see the clear VBI peak here due to built-in voltage, and you can see another peak which is there here, fairly well-defined peak. And we could match it with a single trap. The blue is the simulation-based graph here. We could match it with the 0.37 EV located at a trap at a depth of 0.37 and with a concentration of 1.2 into 10 power 17. Let me show you another characteristics where one could see that there's a distortion, but the effect of trap is not, the peak is not that prominent here. So in this case, our guess was that this is more, perhaps we have a Gaussian kind of a distribution. And this is our initial fit of the characteristics with the Gaussian distribution of traps with the 0.37 EV and with a sigma of 2 kT here. All right, so as a summary of this particular part, what we would suggest is that when you are working with asymmetrical rectifying devices, A very useful plot is simply taking the derivative of the log-log plot. And from there, this is the signature of a good device with a single prominent peak that you see here. And from that, you can quickly get a quick estimate of the built-in voltage. And in case you see satellite peaks, one possible reason that we see for these satellite peaks is the presence of traps. And with some, once you study these peaks in a little bit more detail, you can identify whether they are likely to be due to discrete or exponential or Gaussian distribution traps there. So it's a useful analytical tool to get useful information from the characteristics that we routinely measure. How much time do I have for? Yeah, I'm almost done, right? So I'll quickly go over this last part here. I'll quickly go over this last part. So the point is that we routinely measure these characteristics and we do a log-log plot. And often we take slopes at different places in log-log plots, and we use that to interpret the nature of, to understand what is happening in the characteristics. So for example, in a device like this, when I take a log-log plot and I take a slope and I get v to the power 3.65, and since this is significantly higher than 2, I may conclude that there are traps present in my device and traps are probably filling up. It's only at a voltage of around higher, more than 20 volts or so, that I see a slope of around 2, and I may conclude that traps are all filled and we have trap filled regime here. Now, this log-log plot gives us a grossly mistaken view of what is happening inside the device. Let me show you why. So, for example, as I said, note that at around 2 or 3 volts, traps are not filled. They may be filling up, but they're not filled. On the other hand, if these are simulation results, if I go inside the device and look at my hole density, the trapped hole density. So the number of traps that I've added is 10 to the power 17. And if I look at equilibrium, I find that most of the trapped hole density in the device is small, and most of the traps are empty. On the other hand, if I look at 1.8 volt only, I find that almost all the traps are filled. This is the trapped hole density. And the trapped hole density is almost equal to 10 to the power 17, the total number of traps that were put in. So at a 1.8 volts, I find that most of the traps are filled, while my log-log plot shows that even at 4 volts, I have a fairly high slope and the traps are not filled. And it indicates that you have to go to 10 or 20 volts to fill up the traps. So these log-log plots and simply taking a slope can be grossly misleading. And so what we suggest, and the reason for it is that what we are thinking is, when we are analyzing log-log plot, that our current is varying as k multiplied by v to the power m. So if we are assuming that the characteristics is power law of this particular form, and then when we are taking a slope like this, we are thinking that we will get the factor m here, the exponent m here. On the other hand, a more general view of these characteristics is that it's not k into v to the power m, but it's k v minus a threshold term to the power m. Because the threshold term could be VBI, or it could be the trap filled limit voltage here. So this is a more generalized power law expression as compared to this. Now, if you simply take a slope here, you don't get this exponent m. If you take the slope, the derivative of this, you get m multiplied by v minus vt alpha here. And if v is very close to vt alpha, the threshold point here, you may get a slope which is much higher than what the actual slope in the characteristics is. So you may see a slope of 3.65, while the actual slope may actually be 2. Because you're assuming that the characteristics is of the form k v to the power m, while actually it is of this particular kind here. So what we suggest is that instead of doing a log-log plot and taking slopes, what you should do is you use this particular function here. A function called Vx, because it has the units of voltage here, Vx equal to j divided by the derivative of j with respect to v. If you do that, then you find if you have a characteristics of this form, then Vx turns out to be v minus vt alpha by m here. And therefore you get a straight line, and from the slope of which you can get the true exponent m, and you can get the threshold point here also. So when we take these IV characteristics that you see here, and when we subject it to this kind of a analysis, this is the graph that we obtain here, Vx versus V. And in this case, we see that indeed the slope is 2 in this entire region here. And the actual slope at 2 volts is close to 2, indicating that all the traps are filled. Just as my simulation results had shown that inside the device all the traps are full. And now with this particular analytical tool, we find that this is indeed true. So what we suggest in the interest of time, what we suggest is that you can take this particular function here, Vx, and subject your data to this particular function here. And you find that you can analyze the device in a much more accurate manner using a more generalized power law expression. And you will get a much better expression or estimate of where the trap fill limit in the devices. So which areas of the device are free of traps and which area of the device the traps are filling up. For example, here, the traps are rapidly filling up here. It's almost like a constant region. And this is a region where we get a slope close to equal to 2, almost like that the traps are all filled here. So again, in the interest of time, I will skip some of these. So these are results again from a solar cell here. And so these are the data that you see here. So we see the presence of a single discrete trap. And we are able to calculate where the actual trap fill limit voltage is around 1.25. And from there, we are able to get what the trap concentration likely is. Note that if you had simply taken a log-log plot, you would have concluded that even at around 2 or 3 volts, the traps are not full, while we indicate that the trap fill limit voltage is only 1.25 volt here. I'll leave you with one last graph here, so I'll skip some of them. So this is an ITO P.PSS Pentacene gold device. And this is a log-log plot of it. And so if we look at log-log plot and we take a slope here, it indicates 2.55, and we may conclude that it's almost like a perfect device and with a slightly higher slope because of field-dependent mobility. But when we subject it to derivative of log-log plot, we see that there's an abnormality here. We could see a sort of a trap peak that is located here. And when we subject it to this Vx analysis here, this data here reveals several interesting things. We see that there's a region here with a slope of 2.61, almost like a trap-free with field-dependent mobility here. But then we see a region of slope of around 1.65. And probably what is happening is that the currents are higher in the device here, and the device is getting limited by series resistance, and that causes the slopes to go to a more linear region here. But then there's another region, again, we find there's a higher slope region here, 3.2. So perhaps there's another trap located beyond this particular region here, and so we see a higher slope here. So all of these insights that you see here will be, you'll completely miss them from the IV characteristics if you simply stop and simply look at the log-log plot and start making judgment on the basis of what you see over there. So let me quickly summarize. So what we are suggesting is that the IV characteristics that you measure, you can get some very interesting data, additional data, if you simply look at the derivative of the log-log plot. And this is the signature of a healthy device with one single peak. You can calculate the built-in voltage. If you see additional peaks, a strong reason for that could be presence of traps. And you could make several inferences regarding the traps, the nature of the traps, their location, and their concentration through this analysis. A better analysis of the whole IV characteristics is through this particular function here, Vx equal to J, del J by del V. This takes into account a more general power law expression with thresholds. And with that, you can find the trap fill limit voltages and other regions of the characteristics that are not evident at all in the normal log-log plots. And finally, in the beginning, we suggested that you could use a log of J divided by V plus V beta against the average field to better estimate the mobility parameters. So finally, as a one single sentence summary, well, what you see depends on how you represent it. So in addition to the usual ways of displaying data that you may be familiar with, what we suggest is these 3 additional ways of analyzing your data through this derivative of log-log plot, through this Vx function here, and through this additional plot here, which will yield you more insights from the IV characteristics that you may be routinely measuring. Thank you. Let me stop here and